Welcome back to Easy as Pie, where math is made simple. Make sure that if you're new to the channel, that you hit that subscribe button so you don't miss any new content. Today we'll be covering the Level 3 Calculus Differentiation Paper 2018, Question 3. Part A. Differentiate y equals e to the power of 2x all over x squared plus 1. You do not need to simplify your answer. So all they want you to do here is differentiate this to get dy by dx, and then we're done. It's not too tricky, this question. The only trap that you might fall into is forgetting about the quotient rule. So it's when you've got a function of x divided by a different function of x or another function of x. So we'll just have a look at the formula sheet because that'll tell us what to do there. If we look here, the quotient rule is right here, so I'll just write that out on the other page. It basically says if you've got y and it equals a function of x, f over a different function of x, let's call it g of x, then your derivative, dy by dx, will equal g times f dash minus f times g dash all over g squared. So to keep it consistent with the formula, we're going to put f as our top part, so we're going to make e to the power of 2x f, and the bottom part is g. And so g will be x squared plus 1. So we'll just write that down here. F equals e to the power of 2x, and g equals x squared plus 1. Right, so just looking at the quotient rule, what we need here, we need g, which we have, we need f, which we have, we need to find the first derivative of f here, and the first derivative of g, and then we need to square the g that we already have to put into here. So let's start with finding the derivatives. We'll start with f equals to e to the power of 2x. Exponentials, e to the x goes to e to the x, but e to the 2x is a little bit different. We won't do the full chain rule with the u substitution, but if you want to, this is how you would set it up. You'd go y equals e to the power of 2x, and then u equals 2x, so that y would equal e to the u, and then you'd go through the process. But what's going to happen is that exponentials differentiate to themselves, and then you times the derivative of the power to the front, and the derivative of 2x is 2, so 2 comes to the front, and then f will become f dash, and this one here is pretty straightforward. X squared goes to 2x, and 1 is a constant and goes to 0, and g will differentiate to g dash. The only other thing we need is g squared, so g squared is just going to be x squared plus 1 all squared, which I get from if I squared this side and then squared this side. That's where this part here comes from. I'm just going to remove that stuff here so I don't get confused later. Right, we're ready to plug that into our formula to get the derivative. So dy by dx is going to equal g times f dash. I'm actually going to write it down here. I'm going to get a little bit out of room. Dy by dx equals g, which is x squared plus 1, multiplied by f dash, which is this here, to e to the 2x. Then we've got a minus f, which is that, multiplied by g dash, which is 2x, and that's all over g squared, which is just all of this. Right, and obviously you can simplify this down, but I would leave your answer like this, as the question has told you not to simplify your answer, and there's no point doing extra work if it's just going to waste time, where you can use it elsewhere in the exam. So this will get you an achieved mark. Part B, a curve is defined parametrically by the parametric equations x equals 5e to the power of 2t and y equals 2 times e to the power of 5t. Find the gradient of the tangent to this curve at the point where t equals 0. So all it's asking for us is to find dy by dx and plug t equals 0 into this to get our answer. The parametric equations are on the formula sheet, but the first derivative is quite straightforward, as it's just dy by dx equals dy by dt times dt by dx, and you just think about that like the dt's cancelling out there, leaving you with the dy by dx, and that's what you want there. We'll start with x equals 5e to the 2t. Again, I'm going to do this in short. The u substitution you can make is u equals 2t and then go through the long process, but I'm just going to show the short process here. Differentiating this side with respect to t, because there's a t here. Exponential, so the 5's a constant, it'll stay where it is. Exponentials go to themselves, so e to the 2t will remain e to the 2t, and then we times the derivative out to the front, and the derivative of 2t is just 2, so we timesing that 2 out to the front, which will give us 2 lots of 5 is 10 e to the 2t. And because we differentiated this with respect to t, we have to differentiate x with respect to t. Right, so we have dx by dt, 10e to the 2t. Now let's look at y. Y was 2e to the 5t, so 2 times e to the 5t. We're going to do the short way here. Again, if you wanted to do the u substitution to get dy by dt, you'd make u equal to 5t. The short way of going about it is 2 is a constant, so it'd stay at the front. Exponential, differentiate to themselves, so e to the 5t, and then we times the derivative to the front, so derivative of 5t is 5, so I'm going to times the 5 here, and I'll get 5 2's are 10 e to the 5t. Because I've differentiated all this with respect to t, this is going to get differentiated with respect to t, dy by dt, giving us dy by dt equals 10 e to the 5t. Right. To get dy by dx, we needed dy by dt times by dt by dx from before, and to get dt by dx, because at the moment we only have dx by dt, I just have to flip this upside down, and then I'd have to flip this upside down, so we can imagine this as being over 1 at the moment, because that would still be the same, and then just flipping that upside down. So dt by dx is 1 over 10 e to the 2t. So if we put all that together, dy by dx equals dy by dt is this part here, so 10 e to the 5t, and we'll make that over 1 because that's still the same thing, multiplied by dt by dx, which is this part, 1 over 10 e to the 2t, which equals 10's will cancel, and we're left with e to the 5t over e to the 2t. And we want dy by dx when t is 0, so we're going to replace the t's with 0, which will give me e to the 5 times 0 over e to the 2 times 0, which is e to the, and 5 times 0 is 0, over e to the 2 times 0 is 0. Anything to the power of 0 is 1, so it's 1 over 1, which just equals 1. So that's the final answer there, and that will get you an achieved for that question. Part C, the diagram below shows the graph of the function y equals 15 minus x squared, so that's just the parabola bit around the outside there, inside which an isosceles triangle OAB, so OAB, that triangle, has been drawn. Find the maximum possible area of the triangle. You may assume that your answer is a maximum, so we don't need to prove it's a maximum at the end, which is good. It'll save us some time. And so what we're looking at is an optimization question here, and so the steps for an optimization question is usually to 1, draw a diagram. They've been nice enough to give it to us, and step 2 is write an equation of the thing you're trying to optimize. And in this case it's the area of the triangle, so let's try and write the equation of the area of this triangle. These ones can look quite tricky at the start if you haven't done something like this before and it's a graph, but once you've done a few they make a bit of sense. So I'm just going to show you a few triangles that we could make up. So for example here, that's another one we could make, just to get an idea of what they would look like. Or if we did a wider one down here. So basically what you do is you say, well, this point here is a point on the graph, so I'm going to make it a coordinate x, y. I don't know what the x value is, and I don't know what the y value is, but it's on the graph there. Just like that could be a point xy, or that could be a point xy. And the area of a triangle, we need the base and the height, and we're going to times it by a half. So we're going to get the base and the height in terms of x and y for now. The distance from the origin, which is here, horizontally to that point there, is just x. Like that's the x distance. It doesn't matter where you are, it will always be the x distance to that point on the graph there. And because it's an isosceles triangle and it's been split right down the middle, if that distance there is x, that means this distance here must also be x due to the symmetry of it. So the base of any of these triangles within this graph is just going to be 2x. So the base, let's just draw it out here. Base is going to be 2x for any of these triangles, and the height of the triangle, well, if we look at the little blue triangle down here, the height of that triangle is just from the base up to the graph, so it's just the y value of the graph at that point. Same with this one, up to there it's just the y value, and up to here on the green one it's just the y value of the graph. So the height is y. So if we write the area of the triangle out, it's going to be a half multiplied by the base, which is 2x over 1, multiplied by the height, which is y over 1. Doing a little bit of simplifying, the 2's will cancel, so the area that we're looking for this triangle is just x, y. So we've completed step 2 now of writing an equation of the thing we're trying to optimize, which is the area of the triangle. I'm just going to get rid of this. Step 3 is you need to write the equation in terms of one variable only. At the moment the problem is that we've got x and y which are change dependent on each other, so we must be able to have a connecting equation between the two. So I need to know, like, if x was here, what the y value would be there, or if x was here, what would the y value be there. But luckily we've been given the equation of the graph, which tells us the x value for any y value, or the y value for any x value. So that's the equation we're going to use. That's our connecting equation. Y equals 15 minus x squared, and we can plug that y into here as 15 minus x squared. So the area of the triangle is x multiplied by, and y is 15 minus x squared. We could use a product rule to differentiate this at this point, but it'd be easier just to expand it and then differentiate. So x times 15 is 15x, and x times negative x squared will give me negative x cubed. Right, once you've done these steps, the last step to do is differentiate. Set the derivative to 0 and then solve. So we're going to differentiate this side here. We're going to get 15x is going to differentiate to 15, and x cubed will go to negative, so the 3 will times the front, negative 3x, and take 1 off the power, negative 3x squared, and that's a dash, or dA by dx. We're going to set the derivative to 0 to find what x value will give us a maximum area. Add 3x squared to both sides. Divide both sides by 3, because us x squared is 5. So x must equal plus or minus the square root of 5. And again, because we're dealing with a length here, the negative answer is invalid, so it's just the positive square root of 5. So we're just about there. Remember from before, we've got to make sure we answer the question. So find the maximum possible area. We've just found the base that will give us the x value for the base that will give us the max area, so we still need to find the maximum area. And we know that from up here that the area of the triangle is 15x minus x cubed. So we're just going to plug in our value that we found of root 5, so 15 multiplied by root 5 minus root 5 cubed, and that will give us an answer of, if we get our graphics calculator up, (15 times square root of 5 minus the square root of 5 to the power of 3). And we've got an area of 22.36. And we'll just check for units. No units on here, so we just say units squared since it's an area. And that there will get you a merit for this question. Part D, find the equation of the tangent to the curve y equals x squared multiplied by the natural log of x at the point where x equals e. So this one here, we do have to find dy by dx, the derivative, but not only do we have to find the gradient, we have to use that to help us find the equation of a tangent. So as soon as you see equation of a tangent, the formula that should come into your head, and it is on the formula sheet, is y minus y1 equals mx minus x1. So to get the full equation out of the tangent, the three things we need is the gradient of the tangent line at the point where it touches the curve, and also any coordinate x, y the tangent line itself on the straight line. So just have a wee sketch and just visualize what's going on here. So we've got this x squared of natural log of x, which will be some curve going like this. It's not exactly true, but just for a visualization. Say that point out there's e, because e is roughly like 2.7, and you're looking at the point here on the curve where the tangent line, where a line just touches that point only and keeps going. So to get the gradient, dy by dx when x equals e will give us the gradient of that line, so that will give us the m value that we want over here, so that will give us that. And to get the xy coordinate, because it's a tangent line, it will touch the curve at this exact point. So we know the x value at that point, and to get the y value we can just use the equation here, because it touches the line, so we can use that equation, and we don't have the tangent line equation, so we obviously can't use that to get that y value at this point. So plugging x as e into here, we will find out this y coordinate, which will help us get y1. Y equals, and I'm plugging in x as e, so I'm going to have e squared times natural log of e, which is going to give me e squared is just e squared, and natural log of e is 1, so times 1. So when x is e, this y coordinate is e squared. So our x1, y1 coordinate is e and e squared. And you can get these values out on the calculator if you want them in decimal form, but I'm just going to leave them in exponential form. So the last thing we need to do now, as we've got x1 and y1, is get m, the gradient. So I'm going to start by trying to differentiate this. I'm going to rewrite it down here. Y equals x squared times the natural log of x. Again, there's nothing tricky about differentiating x squared or natural log of x, but the trap is that it is two functions, x squared and natural log of x, multiplied together, so it is a product rule. I'm going to call this f being a function of x and g being a different function of x. The product rule states that if you have y being a function of x times a different function of x, that the derivative dy by dx is f times g dash plus f dash times g. We have f and we have g, so it's time to find g dash and f dash. Right, we'll let f equal x squared, so f dash is going to be, and this will differentiate to 2x. G is natural log of x, so g dash will be, and ln of x goes to 1 over x when differentiated, giving us dy by dx equals, and just following the formula, f is x squared, g dash is 1 over x, so multiplied by 1 over x, and remember we can write x squared as x squared over 1, that'll help us times them together soon. We've got a plus, f dash is 2x, and g is ln of x. Simplifying this down a little bit, dy by dx will equal, we've got an x here that'll cancel with one of these x's, which will just leave us with x, and this here will just be 2x multiplied by natural log of x. And we want the gradient dy by dx for the tangent line when x is equal to e. So let's plug that in. X will be, so it's e plus 2 lots of e times natural log of e. Again, natural log of e is just 1, so we're going to have e plus 2e times 1, which is 2e, which equals 3e. So our gradient is 3e. Let's go back to the start. Right, we're going to write this down the bottom, and we're going to write this down the bottom, and fill in the blanks. Equation of a tangent line is y minus y1 equals mx minus x1. We've gotten the gradient out from before. We had our coordinate on the line was e and e squared. And it's going to plug that in, so y minus y1 is e squared, so chuck that into here. Gradient m is 3e, x is x, they're just the variables, so you leave them as y and x, and x1 is e, so minus e. If you wanted to go further with it, you could go y minus e squared equals 3e times x will be 3ex, and 3e times minus e will be minus 3e squared. Then add e squared onto both sides, you'd get 3ex minus 3e squared plus 1e squared will give you minus 2e squared. But you'd get full marks at this stage anyway, because it did not ask you to simplify. And that will get you a merit for that question there. We've made it to part E, the excellence question, the final excellence question of the paper. The above shape is made from wire. It has both vertical and horizontal lines of symmetry. So that makes life a lot easier, as it can fold on itself this way and straight through the middle this way, meaning this length, these four lengths are the same length. The ends of the shape are the vertices of a square with side lengths of 10 and 10 as shown in the diagram above. The length of the piece of wire through the center of the shape is x. That's shown there, so that length there is x. Find the value of x that enable the shape to be made with the minimum length of wire. You do not need to prove that the length is a minimum. Again, another optimization question, so we just follow the key steps. 1, draw a diagram. We're not going to have to draw because they've given it to us, which is great. Step 2, write equation of thing trying to be optimized. In this case is the length of the bold black wire in the question here. So I'm just gonna tidy this up a little bit. So let's call this y because we don't know what it is, and that makes all of these y because they're all the same length due to the symmetry of the shape. And we're going to write an equation for the thing trying to be optimized. So we want all this black wire to be optimized, and that consists of the length of the wire is equal to 1x plus 4 y's altogether. So that's step 1 and 2 done. Step 3, we need to write equation in terms of one variable. So at the moment it's in terms of x and y, so we need to find a connecting equation between x and y. To do that, we're going to look at splitting the shape in half here. So I'm going to zoom in on here. If I split that in half, because it's all symmetric, that'll cut x directly in half, and this length will be x over 2. And that means that this half of the flag, or the wire shape here, is going to be 5 centimeters now, because I'm cutting that whole 10 in half, which makes this height the difference between 5 and x over 2. So that's going to be 5 minus x x over 2. And this distance here, if I split it straight down the middle, because it's symmetric, if that was 10 the whole thing, then that part must be 5. And we're just going to draw this wee triangle out over here. So I'm drawing that out. I've got 5 as the base, y is the hypotenuse, and 5 minus x over 2 is that side. To get the connecting equation, I'm going to use Pythagoras, calling this side A, B, and the hypotenuse C. Pythagoras is a squared plus b squared equals c squared. So I've got 5 squared plus 5 minus x over 2 squared equals y squared. 5 squared goes to 25 plus, now just be careful with this, because the common mistake is that people just square the 5 and square this part, but it's the same as saying 5 minus x over 2 multiplied by itself again, and then we have to do the expansion of the double brackets, equal to y squared. And we're going to expand this out, so we've got 25 plus 5 5's give me 25. 5 times negative x over 2 is minus 5x over 2. And then again, minus x over 2 times 5 is minus 5x over 2. And x over 2 times x over 2 is x squared over 4, and because it was a negative times a negative, that's a plus, and that's equal to y squared. Simplifying this down a little bit, we're going to have 25 and 25 makes 50, minus 5x over 2 minus 5x over 2 again is minus 10x over 2 plus x squared over 4 equals y squared. And I'm just going to rewrite this in a different order. I just like my x squareds at the front, so I'm going to have x squared over 4 minus 10 over 2 is 5, so we can write this as 5x, and plus 50 equals y squared. And I'm going to square root both sides to get y on its own, or power of a half each side, so y equals all of this, here, to the power of 1/2. And so we're just about there in terms of getting it in terms of one variable. So our length of our wire is going to be x plus 4 lots of y from up here, and that y can be replaced with all of this x squared over 4 minus 5x plus 50 all to the power of 1/2. And we want, once we get it in terms of one variable, our next step is to differentiate both sides with respect to the variable we've got, which is x. And once we get dl by dx, then we can set that to 0 and solve for what our x has to be to make this work, or make it be the max or min value for x, for the wire. So what we're going to do is we're going to differentiate both sides with respect to x. The left is going to be this, and differentiating the right, remember we can differentiate between plus or minus signs. This becomes dl by dx. Differentiating x with respect to x will be 1, that bit there, plus, and I'm going to pull the 4 out to the front here because it's a constant. You can pull constants out to the front because they have nothing to do with x. So we're looking at trying to differentiate x squared over 4 minus 5x plus 50 all to the power of a half. So I'm going to let this equal to y, like we've done in the other questions, just to make it more easier because that's quite difficult at the moment. So I'm going to get y equals x squared over 4 minus 5x plus 50 all to the power of a half, and we're going to do a u substitution to get dy by dx, and then we're going to plug that in as the derivative here. Right, we're going to let u equal x squared over 4 minus 5x plus 50, which will then give us y equals u to the power of a half. U equals, actually not u equals, we're going to differentiate, so x squared over 4, the 2 is going to come to the front, so we're going to get 2x over 4. The minus 5x will differentiate to minus 5, and the 50 goes to 0 as it's a constant. I differentiated this side with respect to x, so this has to be du by dx. And we can call that 1 over 2x minus 5, because 2/4 of x is the same as half of x. This one here, the half comes to the front, and we minus 1 off the power, so it's going to be negative 1/2, and that's dy by du. Right, so to find the derivative of this thing here, so we can plug it back into what we were doing before, we need dy by dx. So with the chain rule, that's going to be dy by du multiplied by du by dx, and we're just going to think about that like the fractions cancelling, leaving us with what we want, dy by dx. Plugging in the things we have, we're going to have dy by du is this part here, 1/2 u to the negative a half, multiplied by all of this here, a half x minus 5. So I'm going to make that look a lot neater. So we've got 1 over 2 multiplied by, and u to the power of negative a half is 1 over u to the power of positive a half, multiplied by x over 2, because that's just x over 1 times a half, minus 5 over 1, which equals, this part here is going to be 2 times u to the power of a half on the bottom and 1 on the top, multiplied by x over 2 minus 5 over 1, which gives us, and we times this through, we're going to get 1 times x is x on the top, and 2 times 2 is 4, and then we've got the u to the half, minus 1 times 5 is 5, and 1 times this is itself. And that's dy by dx. One more thing that we can do, just to make it a little bit more simple, is times this by 2 over 2, because if we times anything by a number over the same number, that's just 1, and if we times anything by 1, it's still itself. And the reason we would do that is so that we can get the denominators the same, so it's easy to go across. So this becomes 10 over 4u to the power of a half, and now that the bottoms of the fractions are the same, when we subtract fractions, the bottom stays the same, and we just subtract the top, so it's x minus 10 on the top. So that's my dy by dx here, which gives us dl by dx equals, and dl by dx is the derivative of the length of the y, which we were doing from the start. So dl by dx is all this stuff here. So we're going to have 1 plus 4 multiplied by the derivative that we just found. So 1 plus 4 multiplied by the derivative that we just found, and that was x minus 10 over 4u to the power of a half. And that's 4 over 1, so what we do notice there is that if I times that 4 through, that they would cancel out. So we're left with dl by dx equals 1 plus x minus 10 over u to the power of 1 half. Right, we're now going to set both sides to we're going to set the derivative to 0, but before I do that, I'm just going to re-plug in u. Well, actually, I will set this to 0 and we'll plug in u back in terms of x later, otherwise it's going to take up a lot of space with all the x's. Right, set the derivative to 0, and we're going to start trying to solve for x. Right, subtract 1 on both sides, so we're going to have negative 1 equals x minus 10 over u to the power of a half. Multiply both sides by u to the power of a half, so I'm going to have negative 1 times u to the power of a half is negative u to the power of a half, and timesing this side by u to the power of a half will cancel it, giving me x minus 10. Times both sides by negative 1, that will make this positive, and timesing this by negative 1 will make this 10 minus x. Right, I'm going to plug u back in terms of x now, so it's going to go find out what it was. And here it is here, x squared over 4 minus 5x plus 50. X squared over 4 minus 5x plus 50, and that's all to the power of a half equals 10 minus x. We're going to have to square this whole side to get this power of a half going, and then we'll have to square this side, so we're going to be x squared over 4 minus 5x plus 50 equals, and then we're going to have to square this. Remember, it's the double brackets, not just squaring each individual term, which is a common mistake. Which will give us 10 tens are 100, 10 times negative x is negative 10x, minus 10x again, and negative x times negative x is positive x squared. Right, I'm just going to simplify down, so I'm going to have x squared over 4 minus 5x plus 50, and the right hand side I've got two like terms here, so I'm going to have 100 minus 10x is minus 20x, and then plus x squared. Right, now what we're going to do is I'm going to, just to get rid of that 4 on the bottom, because fractions are really annoying, I'm going to multiply this side here by 4, and then I have to multiply this by 4, and the reason I'm doing that is so that 4 will cancel this 4 out. This 4 will cancel this 4. Timesing that through, 4 times this, that will cancel the 4, giving me just x squared, and then I have to times it all the way through, so 4 times negative 5x is negative 20x. 4 times positive 50 is 200. 4 times 100 is 400. 4 times negative 20 is negative 80. and you got the x there too, and 4 lots of x squared is 4x squared, and that just makes it nicer because now I don't have to worry about that fraction anymore. Right, we've got a quadratic to solve, so we need to set one side to 0, and then we can just use our quadratic formula in the calculator, and we're there. I've got to bring this x squared over to here, so I'm going to minus x squared on both, minus an x squared on both sides. I'm going to add a 20x on both sides, and I'm going to subtract a 200 on both sides. This whole side will go to 0. This here, 400 minus 200, will leave me with 200. 20x minus 80x will give me negative 60x, and negative x squared plus 4x squared will give me positive 3x squared. And I'm just going to write it in the form of x squared, x and then the constant, so it's going to be 3x squared minus 60x plus 200. That's your A, negative 60 is your B, and C is your 200 when you put it into your quadratic formula. So if we go into equations, this one here, polynomial f2, degree is 2 because that's our highest power, 2, f1, and chuck in A, B and C, we get 3, negative 60, and 200 for C, and we get x values of 15.77 and 4.23 if we round it to 2 decimal places. So we're going to have to investigate that, see why we're getting two values, see if they both make sense or if only one makes sense. So we'll just get our length back up in terms of x. Just trying to find it. Oh, here it is here. L equals x plus 4 times x squared over 4 minus 5x plus 50 to the power of a half. L equals x plus 4 lots of x squared over 4 minus 50x plus, I'll just check that again, sorry, minus 5x plus 50 to the power of a half. Minus 5x plus 50 all to the power of a half. Right, let's check them out. So we'll check it out when x is, we'll check for x is 15.77 first. 15.77 plus 4 lots of 15.77 squared over 4 minus 5 lots of 15.77 plus 50 to the power of a half. Chuck in the calculator. 15.77 plus 4 lots of a quarter times 15.77 squared minus 5 times 15.77 plus 50, and that's all to the power of 0.5, which is a half, and we get a length of 38.86, and then we'll check it for x is 4.23. 4.23 plus 4 lots of 4.23 squared over 4 minus 5 lots of 4.23 plus 50 to the power of a half. And I'll re-go through that. So we've got 4.23 plus 4 times a quarter of 4.23 squared minus 5 times 4.23 plus 50 to the power of 0.5, and we get a length of 27.32. So the two solutions we've got, this one must be the maximum, we don't have to prove it, but that one must be the maximum, and this one must be the minimum. And so that's the one we wanted the minimum length. So when x is 4.23, that must be our solution. Just in terms of that x value that we got out, the 15.77, if we actually look back at the question, is it possible for x to be 15.277, because this length is 10 and x is less than 10, so we can actually ignore that solution because it doesn't make any sense. So that one there, we're actually going to ignore it, so that's invalid. So make sure you show the examiner that's invalid, because x has to be less than 10 or it doesn't make any sense. So that is the correct answer there, and that one will get you your excellence.